Chapter 9 deals with analyzing energy balances that occur for reactive processes. To begin this chapter, I want to give a short introduction. And so as we learned in Chapter 4, during a chemical reaction, the chemical identity of a reactant or reactants changes and it becomes a product or a variety of products. And so during this chemical reaction, or during any chemical reaction, what happens is that the bonds that hold the reactants together, those are broken. And so the chemical bonds of reactants are broken, and the chemical bonds of the products are formed. Now, throughout this reaction, energy is transferred. And so in order to break the bonds of the reactant, energy needs to be put into the system. And so energy is required to break bonds. And in order for the bonds of the products to be formed, energy needs to be released from the system. And so energy is released when bonds form. And so if you sum up all the energy that's put into the system to break the bonds, and you also add in the energy that's released when those bonds form, what you get is called the enthalpy of reaction. And so this net energy that is absorbed or released during a reaction is known as the enthalpy of reaction. Of reaction. And we abbreviate this as a delta H sub R. And so this delta H of reaction, this is going to tell us, it's going to play a major role in any sort of reactive process. So delta HR plays a major role in a reactive process. For instance, let's say that a reaction either gives off a large amount of heat or it absorbs a large amount of heat. What this is going to do is this is going to cause a large temperature change in the system. And so this delta H of R can lead to large temperature changes, What's also important about delta H of R is that if we're able to measure it, we could also use it to calculate important information about the reactants or products that are involved in the reaction. And so it could tell us chemical info about the reactants and products. And to show you an example of this, I want to tell you a short story. And the story is going to be about a scientist named Emmett Chappell, and what he did is he developed Emmett Chappell he developed a method that allows us to determine if there's life on other planets. So he developed a method to detect on other planets. And to do this, all we have to be able to do is measure delta of H of R by measuring okay? And so to give you a bit of background about this story, I want to jump to my other slides for a bit, and I want to show you some pictures. And so the photo in the top left there, that's Dr. Emmett Chappell. Back in 2007, that's a photo from when he was being inducted into the National Inventors Hall of Fame. The photo in the bottom left here is also of Dr. Chappell, but this is back in 1942 when he was in his early 20s, so about y'all's age. And so throughout his career, Dr. Emmett Chappell was a fairly prolific scientist, and he made numerous discoveries that had a huge impacts on biochemistry. But perhaps his most productive period was when he worked as an astrochemist for NASA in the 60s. And in 1966, he was a part of a project that was supposed to develop tools for the Mars Viking spacecraft. And these tools were supposed to help us determine if there were any sort of living organisms on Mars, so help us determine if there was life on other planets. And so on this project, Dr. Chappell spearheaded research into the molecule luciferin, which is a molecule that's found in fireflies. And so during this project, what Dr. Chappell discovered is that luciferin reacts with both oxygen and also ATP, which I have circled there in red. And so ATP is adenosine triphosphate. That's the energy storage molecule that's found in all living organisms. And so with this reaction, luciferin reacts with both ATP and oxygen in order to form oxyluciferin and various other products. Energy is required to break the bonds of luciferin, and energy is released when the bonds of oxyluciferin are formed. And so this net change or net transfer of energy results in the enthalpy of reaction. Now, some of this enthalpy of reaction is released as heat, but there's also a significant portion that's released as light. And that's actually why fireflies glow at night, is because this reaction is continuously occurring within their bodies, and they're continuously emitting this light. And so Dr. Chappell not only discovered that luciferin underwent this reaction, but he also realized that if you're able to measure the light that's emitted from this reaction, this also allows you to calculate the amount of ATP, or the concentration of ATP, that was involved in this reaction. And so, based on this principle, if you wanted to build a spacecraft to detect life on other planets, what you would have to do is put a detector on the spacecraft that's able to measure the wavelength of light that's emitted from this luciferin reaction. And if your spacecraft flies over the surface of a planet and it's able to detect this light, that tells you that not only is there ATP present on the surface of the planet, but that there's also living organisms on the surface of this planet. Now, this discovery not only had a significant impact on, interstellar travel, but also had a significant impact on other branches of science. And so, for example, based on this same principle, what you could do is you could also detect if there are cancerous tumor cells within the body. And so, just by measuring the enthalpy of reaction of a reaction, you're able to get deep insight into the various processes that occur throughout the universe. And so, in Chapter 9, what we're going to do is we're going to learn how to use this delta H of R. We will learn how to use delta H of R. So we'll not only learn how to calculate it, but we'll also learn how to manipulate it within the energy balance. And by doing that, that's going to give us insight into a variety of chemical processes.